Hello everyone. Today we're solving the find missing number problem. Here's the problem statement. Given an array of n-1 numbers ranging from 1 to n, find the one missing number. Let's look at an example to understand this better. We have an array with 4 elements, 1, 2, 4, and 5. The range is from 1 to 5, which means we should have 5 numbers total. But our array only has 4 numbers. Notice that the number 3 is missing from the array. So the answer is 3. This is a classic interview problem that tests your understanding of arrays and mathematical thinking. Let's explore efficient solutions to solve this problem. Let's look at our first solution using the sum formula method. This is a mathematical approach that's very elegant. The key insight is using the formula for the sum of numbers from 1 to n, which is n times n plus 1, divided by 2. This formula is highlighted in yellow for emphasis. Here's the logic in 3 simple steps. Step 1. Calculate the expected sum using the formula. This gives us what the sum should be if all numbers were present. Step 2. Calculate the actual sum by adding all the elements in the given array. Step 3. The missing number equals the expected sum minus the actual sum. The difference between what we should have and what we actually have is our missing number. This solution has big O of n time complexity because we need to traverse the array once to calculate the sum. The space complexity is big O of 1 because we only use a few variables. Let's see this method in action with an example. Let's walk through a complete example using the sum formula method. We have an array with 7 elements, 1, 2, 4, 6, 3, 7, and 8. Notice they're not in order, which is common in this problem. Step 1. Identify n. Since we have 7 elements and 1 is missing, n equals 8. The range is from 1 to 8. Step 2. Calculate the expected sum using our formula. Expected sum equals 8 times 8 plus 1, divided by 2. That's 8 times 9, divided by 2, which equals 36. Step 3. Calculate the actual sum by adding all array elements. 1 plus 2 plus 4 plus 6 plus 3 plus 7 plus 8 equals 31. Step 4. Find the missing number by subtracting. Missing number equals expected sum minus actual sum, which is 36 minus 31, equals 5, shown in green. So the missing number is 5. This method is simple, efficient, and easy to implement. Next, let's look at an alternative approach using XOR. Now let's explore an alternative solution using the XOR method, which is a bit manipulation approach. First, understand the XOR properties that make this work. Property 1. Any number XOR itself equals 0, highlighted in yellow. Property 2. Any number XOR 0 equals itself. These 2 properties are the key to this clever solution. Here's the logic in 3 steps. Step 1. XOR all numbers from 1 to n together. Step 2. XOR all elements in the given array. Step 3. XOR both results together to get the missing number. But why does this work? Look at the blue box on the right. When we XOR numbers from 1 to n, and then XOR the array elements, all numbers that appear in both places will cancel out to 0 because a number XOR itself equals 0. The only number that doesn't cancel out is the missing number because it only appears once in the range 1 to n, but not in the array. This solution also has big O of n time complexity and big O of 1 space complexity. A big advantage of this method is that it has no overflow issues with large numbers, unlike the sum method. Let's understand this step by step next. Let's understand how XOR works step by step. The rule is simple. When bits are different, the result is 1. When bits are the same, the result is 0. For example, 3 XOR 3 equals 0, and 0 XOR 1 equals 1, shown in the yellow box. Now, let's XOR all numbers from 1 to 8. We start with result equals 0, which is 0, 0, 0, 0 in binary. First operation, 0, 0, 0, 0 XOR 0, 0, 0, 1, which is 0 XOR 1. The result is 0, 0, 0, 1, which equals 1 in decimal. Second, 0, 0, 0, 1 XOR 0, 0, 1, 0, which is 1 XOR 2, giving us 0, 0, 1, 1, which equals 3. Third, 0, 0, 1, 1 XOR 0, 0, 1, 1, which is 3 XOR 3. This equals 0, 0, 0, 0, which is 0. Fourth, 0000 XOR 0100, which is 0 XOR 4, giving us 0100, which equals 4. Fifth, 0100 XOR 0101, which is 4 XOR 5, giving us 0001, which equals 1. Sixth, 0001 XOR 0110, which is 1 XOR 6, giving us 0111, which equals 7. Seventh, 0111 XOR 0111, which is 7 XOR 7. This equals 0000. Eighth, 0000 XOR 1000, which is 0 XOR 8, giving us 1000, which equals 8. Following this pattern through all 8 numbers, after XORing all numbers from 1 to 8, the final result is 1000, which equals 8, shown in the large yellow box. Now we'll XOR this result of 8 with all the array elements to find the missing number. Now, let's continue with step 2. From the previous step, our result is 1000 in binary, which equals 8 in decimal, shown in the yellow box. Now we XOR this result with each element in our array. The array contains 1, 2, 4, 6, 3, 7, and 8. Let's go through each operation carefully. First, 1000 XOR 0001, which is 8 XOR 1, giving us 1001, which equals 9. Second, 1001 XOR 0010, which is 9 XOR 2, giving us 1011, which equals 11. Third, 1011 XOR 0100, which is 11 XOR 4, giving us 1111, which equals 15. Fourth, 1111 XOR 0110, which is 15 XOR 6, giving us 1001, which equals 9. Fifth, 1001 XOR 0011, which is 9 XOR 3, giving us 1010, which equals 10. Sixth, 1010 XOR 0111, which is 10 XOR 7, giving us 1101, which equals 13. Seventh and final, 1101 XOR 1000, which is 13 XOR 8, giving us 0101, which equals 5. The missing number is 5, shown in the green box. Now let's understand why this works. Each number from 1 to 8 appears in both operations, once when we XORed 1 to 8, and once in the array. Except for 5. The number 5 appears only once, in the range 1 to 8, but it's missing from the array. Because of the XOR property that a number XOR itself equals 0, all other numbers cancel out, leaving only 5. This is the elegant beauty of the XOR method. Let's look at the code implementation for both methods. On the left, we have the sum formula approach. First, calculate n as array length plus 1. Then compute the expected sum using the formula n times n plus 1, divided by 2. Calculate the actual sum of all array elements. Finally, return expected sum minus actual sum, shown in green. This gives you the missing number. On the right is the XOR method. Start with n equals array length plus 1. Initialize result to 0. Loop from 1 to n and XOR each number with result. Then loop through the array and XOR each element with result. Return the final result value in green, which is your missing number. When should you use which method? Use the sum formula when you want something simple and easy to understand. It's best for beginners. However, there's a risk. This method can overflow if n is very large, because the sum can exceed the integer limit, shown in red. This is where the XOR method shines. Use the XOR method because it has no overflow issues. Why? Because XOR operates bit by bit and never adds or multiplies values. The result always stays within n's bit range, making it safe for very large numbers. This is a crucial advantage in production code. The key takeaway: both methods have big O of n time complexity and big O of 1 space complexity, but XOR is safer for large n. This is a very common interview question, so make sure to practice both approaches. Now you understand why XOR is the preferred solution for large numbers. Thank you so much for watching this tutorial. I hope you found this lesson helpful and easy to understand. If you enjoyed this video, please hit the like button. It really helps the channel grow. Don't forget to subscribe to the channel for more beginner-friendly programming tutorials and helpful tips. Feel free to comment your questions or thoughts below. I love hearing from you, and I try to respond to every comment. And don't forget to hit the bell icon so you get notified whenever I upload new videos. See you in the next lesson.